Okay. So yeah, thank you. It's really my pleasure to drive down here. This is my second Saturday actually, and it's such a great thing in the whole art community. And so I like to thank the organizers, all the volunteers here, and the sponsors for making this available. I do want to thank our core, CRAN, the people that checks your packages and say, please retry again. All the developers out there and all users and all the great feedback. I'm doing a lot of development, and whatever feedback it is, it's always good. So don't hesitate to send feedback. And I also would like to mention our consortium. I have a grant there since last year. I'm not going to talk about it here, but it's basically a testing framework for this on top of what I've already done. Okay, so just to check here. So this is about, I say, parallel and distributed processing in R for everyone. It's more than that too. I will want to see here how many people have done parallel processing in R. Okay, how many people of you who didn't say yes here now, how many think you will do it in the next 2 years? Okay, so yeah, let's just get me an idea. So I will try to do a small introduction here, even if you don't know about parallel processing at all. So the main reason people turn to parallel processing is you want to speed things up. And that speeds things up means looking at the wall time and saying, I want to be finished this afternoon instead of end of the week. And another reason is that sometimes you can't do all your computations on your local machine. So you need to distribute your computations because you run out of memory. You can also distribute it over time, of course. Another thing is like the data transfers are too big, and the astronomers has that problem. They bring down so much data so they can't send it over to the central computer. So they sometimes have to pre-process on site. And there are other reasons too. People are using Shiny, for instance. There's a asynchronous framework there. There's like a parallel backend to that. And I should also say that, I shouldn't say don't parallelize, but don't jump to parallelization as a solution if something is slow. That's not your first thing. There's often things you can, as performance improvements like vectorization and things. There's a lot of things you can do before doing parallelization. So please be aware of that. Okay, so I will start with a very simple example that might give you the gist already at this slide, what the talk is going to be about. But imagine you have a list X here with 4 elements, A, B, and C, and they all, and D, they contain integer vectors, and we want to calculate the sum of each of these elements. So if you do it the manual way, the first time user in R, and you want to store it in a list, you might do something like this. You allocate a list, and then for each of the elements, you calculate the sum. Okay? And then the next step is say, okay, if we have a lot of elements, this is a tedious way, we can for loop over this. So we for loop over the names in the element X, or the vector list X, and you assign it back to the list Y. And then you might know about this. Lapply, or list apply on X, and apply this function sum to all the elements and assign it back to Y. And that will return the same list. So all these give the same results. If you think about this, if you're all interested in the Y and not how we got there, the ordering how we sum up A and B and C, we can do it D, C, A, as long as we just keep track of the order in the end. So but lapply, when you have inside here, we don't really need to know what's going on, in what order is happening. And they actually claim that too. It's like, don't pay attention to the ordering here. It's applying this to A, B, and C. And that's, in sense, it's called concurrency. We don't care about these 4 different units in what order they are processed. And that's the first step. If we have such a problem, we can parallelize things. So how do we parallelize things in R? So this is the same problem. And now imagine instead of the sum function, we have a very slow implementation we call slow sum. So this is a toy example, but each of these elements will take 1 minute each to calculate the sum for. So since 2014 in R we have the parallel package, which has MCLapply, which resembles our original lapply, and it will use the forking processes in operating systems. So that's why it only works on Unix and Mac, but not Windows. So on Windows this will fall back to be a regular lapply. But this is how you, as a developer, say you're going to replace your original lapply with an MCLapply, and you say I'm going to do this in 4 parallel workers at the same time, so 4 times faster. So if you're on Windows, there's another solution that also works on Mac and Unix. You can create a cluster of background R processes. So here I create 4 background workers, and now you have to tell each of the workers that I have a function called slow sum. I pass it over to them, and then I call par lapply. So all these give the same thing here. Okay, quick questions. Any clarifications? Chip?
Does Microsoft R do parallelizing out of the box?
No. So you have to do this yourself. Yeah.
Even the Microsoft?
Yeah. So there are very low-level things that you can do, matrix inversions and stuff. I'm not talking about that. So that's yeah, good question. Okay. So what's the problem with this? You quickly, as a developer, start saying, okay, which of these APIs should I use? And then you start, okay, am my users in Unix or Windows, or both? Do I have to support both? And then testing. You try it on one, but you forgot to test another platform. So it's complicated. And then users, you say, I see the number 1 here, like weird. It works for me, but it doesn't work for you, and vice versa. And that's because people are on different platforms. So when people try to help each other, it doesn't work exactly the same. And sometimes Windows is left out because it's complicated and things like that. Okay, and code, if you want to support everything, you start doing things like this. So you want to have a function that just do an lapply, but you also want to support it to do in parallel. If you're on Windows, you do one way. Otherwise, you do another thing. And this is only covering parallelization on your local computer. If you want to run on 2 computers, you have to add more code. So you can imagine this is very hard to read. It becomes error prone due to test coverage and everything, and so on. So there are approaches to encapsulate this problem to hide it. And one beautiful solution is the for each package, where you as a user say register do MC, that's for here, that's basically fork processing. So the user can decide that, and you as a developer can write the code the same way. For each element in capital X, you calculate slow sum. And then if a Windows user come about around here, they can initiate, before calling your function, they can do this. So they create 4 workers, background workers, and use those as parallelization. And unfortunately, there are some hiccups here. You're probably going to see this because the developer forgot to say that you need slow sum too. So that's the proper way to write that code. Okay, so, but the idea for each is very beautiful and it works well. Okay, so I just want to add a little bit of credentials to what I'm saying here. I started using R, I switched over a weekend basically after being very fluent in MATLAB. And when I saw R in 2000, I switched immediately because of the open sourceness. I, computer science background, applied statistics too. I'm very applied in biology and genetics. So we've been doing methodology in statistics, copy number analysis, DNA, where we have collaborators all over the world. Some are very savvy, some are compute clusters, some has a Windows machine down the hall in a wet lab, and they have to do real analysis. So the methods we develop in statistics, we implement them in R, and we wanted them to run everywhere. So I always have the cross-platform thing in mind. Plus, we also want to be able to scale it up, where we can scale it up in the compute cluster. So in various iterations of like trying to wrap and hide parallelization, in 2015 I said, okay, I want to do the thing I wanted to do for a few years, and that's the future. So all parallelization methods has something in common at the bottom, and that's what I think I identify those building blocks. And of course, like everything else, someone else invented it before you, and this is something that comes mid-70s, different people, and maybe there's someone before that. But so in programming, the concept of a future is an abstraction of a value that will be available later. And that value is the result of evaluating an expression, an R expression. And also, the state of the future is either unevaluated or evaluated, or non-resolved or resolved. So let's put an example to that. So imagine the regular assignment in R. We have a left-hand side and a right-hand side, and the right-hand side can be a simple function call, it can be 1 + 1, or a very complex R expression. And when R sees this line, it evaluates that expression and immediately assigns it to a variable in R. But there are actually two steps going on here. So if we do this in the concept of a future, we can imagine it like in two steps. So we have the expression, and we say create that as a future and keep a reference to it. And then if we emulate R, we say immediately after that, ask for the value and assign it to B. Okay. So I will get to the why this is useful, but that's the essence of a future. And that actually, this is actually code. Of course, you need to put 1 + 2 or something there. Okay, so, oh, this is my, let's see if this works here. I have a package, I will get to it. It's called the future, so you load the library. I'm going to decide how I parallelize now. So I'm going to use you guys for this. And I did create two futures. Here they are. So I can give them out. You can pass them down if you want to, because now they are out of my thing. I know the future 1 there, the future 2. Feel free to pass them around or keep them. So inside there's a calculation of each. Okay. The thing here now, except for the overhead of handing them out, these future now live here, and they are going to be resolved or evaluated. And I still have my prompt here, so I can keep doing my thing, which is giving a talk. Okay, so I'll get back to those two. Okay, so let's go back to the slow sum function. So here is the example of calculating the sum 1 to 100. And this will take 2 minutes, and we know 5050. So the step to parallelization is that the fact that the algorithm sum can be split up in 2 parts here in the data, and then added together later. It's the problem has that property, allowing us to split it up. So we can calculate the sum of the first 50. That will take now half the time, 1 minute, and assign it to A. We can calculate the sum of the last 50 and assign it to B. And afterwards we can do A plus B and get the result again. So we didn't gain anything yet, but we showed that we can split up the problem in a divide and conquer approach. So the future approach to this will be like this. So loading the package, saying, I want to do this in multiprocessing, that means parallelize on your local computer. Now create a future for the first, slow sum, and keep track of that in the future A. And this is now instant. Just like me handing it out, it doesn't cost me much. And I'm back to my prompt. I can do the same for the next calculation. And I can still work with my R prompt. And if these now take 1 minute each, and I work here and do other things, and after like 45 seconds, I say, give me the value of the first one. That's not yet done. It will take another 15 seconds before it's done, so it will block 15 seconds, and then I get the value. And if I ask for B again, that's probably done within the same time frame as A. So there I have, and I can sum them up like this. You see the idea here? No? Yes? No? So imagine these futures I'm passing out here, and someone is doing math. Yeah?
Did you say that when you request the value, it's actually blocking at that time?
Yeah, here.
Okay, so if it's not evaluated yet,
Yeah, it will wait. There is a way to ask if you're done, and you can skip. Yeah.
Am I right in assuming the benefit to this is the simplified syntax? You can like store essentially function, like future function calls, so that you can include them in your code, so you don't have that big messy block that you showed earlier. It's simplified.
Yeah, it's trying to hide the concept of parallelization, but it's, I will get to it soon. I hope I get to it, but it's a good one. Yeah, so that's the, I call it the explicit API to create this. And by the way, there's nothing magic hacking in R here. This is pure R going on under the hood. There's no native code, nothing here. So there is also this operator to make it more similar to the original one, which I call the future assignment operator. And it works because it creates a future for you here, and then it assigns it to what we call in R a promise. As long as you don't touch the promise, nothing will happen. But as soon as you touch it, things will happen. It's a little bit magic, but there's, if you heard about delayed assignments in R, that's what's happening underneath. Okay, so this is what the same code would look like if we used the future assignment instead. So it's almost like the non-parallel version. It's just that special assignment operator. And it's only when I try to touch A or B here now, it will block if it's not done. And if it's done, it won't block. And I waited long enough, so it was already done. And at this point, when you touch them, they are regular variables. There are no more futures involved. So a little bit of magic, but... Okay, so this is what I handed out. I handed out 2 pieces of papers with this, and I basically asked to calculate the sum of these two, and it gave me a talk. Now we're here, so let me see, where's future 2? Who's holding on to the future? Okay, they're not meant to leave the room. Okay. Do you have it?
No, it's
in the back.
Okay, so thank you. And future 1. So this illustrates another problem with parallelization. I love the microphone. With parallelization comes overhead. So if your calculations is very fast, it's not worth doing this. So what's inside here, if it takes a long time, is worth doing. And you can parallelize on your local computer, but what I'm saying here, it can actually be sent to the other side of the world and back here without you changing the code. So overhead is always involved. So, and I got 11 here, 20, and that. But do you see the point of the future? I almost lost one, but yeah. Which can also happen. Okay, so there are many ways to resolve futures. You can do it sequentially. That means your code will work like as if you didn't parallelize. You can say run it in parallel in your local computer. You can have 3 local machines in your local network, N1, N2, and 3. You can also have remote machines. You can actually set this up so it's automatically SSH in and all that things. But this is actually actual code that could work. And regardless of that, you will always write the same code and just get the same answer. Okay, so the package is on CRAN since 2016, I think. The idea is write once, run anywhere. We're trying to find the essence of parallelization in the API and not more, not less. Works on all the operating systems. Super easy to install, well tested. We use it in real research. And I would say several hundred terabytes of data being processed this way in my projects. And I should also say it's, I forgot that in my very first slide. There are, not all parallelization problems falls into this. They're like distributed data storage and all that stuff. That's not what I'm trying to attack here. So I'm not trying to claim it solved everything. Okay. It builds on top of the parallel package, which in turn builds on legacy packages, Snow, RMMPI, and network spaces. I wrote the globals package to find global variables. This one is a parenthesis, we don't have to discuss that. But it provides a very basic API to create futures, get their values. Okay, so why this? It's, I hope to say it's like encapsulate that problem of like you having to worry about which backend should I use. You just need to focus on what should I parallelize. And also for the end user, the user can say, hey, I got more than one machine. I have multiple machines, so I can use that instead. So the model is you decide what to parallelize, the user decides how. And it works for most problems. And to your point here, it provides building blocks. With those building blocks, we can do much cooler things on top of that. But I think these are the atomic building blocks for parallelization. And you can build new backends pretty easily that supports this API. So there are some for compute clusters, schedulers, Google Cloud Engine and things like that. Okay, so another thing I want to point out, I wasn't sure if this should go in the beginning or not, but actually turns out to be working pretty well to automatically identify functions and packages and variables that you need to make sure you pass along to the workers. And the idea is like basically it's for code inspection, code tools. So the future expression here is a bracket, slow fun, and you pass the object X. And code inspection is like in the computer world, it's an abstract syntax tree. So R sees that, and it decides that the curly bracket is a base function. I don't need to pass that along. All R instances has that. The parentheses there indicate a function call. And then it sees two objects, slow sum and X. So it knows that it needs to pass on the slow sum function, unless it sits in a package on the worker, and also the data. So that's taken care of automatically, but if you don't trust this, or you think there's too much overhead in that, which is not very much, you can always specify manually too. So, questions? Yeah?
You mentioned support for schedulers. Is that currently done, or is that something you have to write yourself?
Support for?
For scheduling on the cluster? Is that just
soon.
already?
Yeah. No, it's done. I will show you soon. Good question. The question was schedulers and compute cluster. Yeah.
One problem I've had in the past is parallelizing and then each call going out to some external library that then fails silently and
doesn't return an error. So if you lost the sheet of paper and it had not made its way back to you, how would your code know? And can you ask it, is this dead?
It depends on the backend. It can detect it. There is a framework to detect it. There's no, this is a frequently asked feature request. It's like, can we retry automatically and things like that. That's not there because it's dangerous to try to promise that, but we're working on it. Okay, so, okay, one more question.
If it's not entirely my code, for example, I use the currents package
Yeah.
for hyper parameters optimizing. I would like, these are totally independent runs. How do I tell Keras that this is?
I will actually get to carrot example, but it's like just an example, but maybe we, yeah. Yeah. So with these building blocks, I didn't mention there's a function called resolved. You can check if a future is resolved and you get true or false, so it won't block. With those 3 building blocks, you can build bigger things. So here's like how you could do your very first own parallel lapply. And this works. It's not the most optimal, but it works. You basically create one lapply where you create the futures with the function calls you want to have. And then at the end, you say, give me the values. So those futures you create on top, they will run in parallel if the user said, I will want the parallel backend. So this is actually a function that works. And then you can use that everywhere, Windows, Mac, whatever. Okay. So, and this was like the first proof of concept, but then people start asking for it. It's like future.apply package. It provides future versions of all the base R apply functions. Well tested. So if you have an lapply function statement and you want to parallelize that, you just replace it with future_lapply. And then quickly people start asking about the per. You can parallelize those. And David, I don't know his last name, Vaughan, he went ahead and implemented this. So if you have a per map function, you can just do future map function. Okay. And then for the for each, we wrote the do future backend. So that basically means that any future backend that exists now or in the future, sorry for the pun, will be compatible with for each calls. And that one, the very first implementation was like 30 lines of code. It was because of these atomic building blocks. They did everything. And now, because of that, so 2 points here. There is a package I mentioned, which is called the future.batchtools package, which provides you to parallelize in a compute cluster job schedulers. So with the do future package, and together with that, there are now 1,400 packages on CRAN that you can, instead of parallelizing a local machine, they can parallelize in a compute cluster. Because those packages are using for each internal. So that just came for free now. So this is the example. You can, in Carrot, if you don't specify anything, and if you don't register it for each backend, it will run sequentially. And here, so your question was here now, can you, with this approach here now, I claim you can just say, you can register a parallel backend and Carrot will run in parallel. Did that? Oh, Keras, sorry, I thought you meant this Carrot. Okay, okay, sorry. I don't think that, I don't know enough about that, so I don't know. Yeah, we can talk about it after. Sorry, I thought you said Carrot here. Okay, okay. Okay, so high performance compute clusters. Hands up if you're interested or have done this or think you might do it in the future. So So 10 people, 15, yeah, okay, thank you, 16. So I'll give my background to it. Like, so I work in genomics mostly. So the genome has like 3 billion base pairs, ACGT. This is a project with 80 patients, tumor, cancer. But the very basic thing when you do a study with genomics these days, you sequence data, you get lots of small reads, and you want to map them to a reference genome. It's a tedious task, and that can take a very long time. In this example, it's 3 hours per individual, and the data is 200 gigabytes per individual. And if you would do this in R with an lapply, this is the outline what that function would be. The data sits in files, so you get the names of the 80 files here, and then you call a special function in DNA-seq package called align, and they will step through them one by one. So 3 hours each will be a good 10 days of processing here. Okay. Now with the future lapply, if you have a 12-core machine, now all you have to do is replace that lapply with future lapply, and you specify what backend you have, multiprocess. And that's a reminder, time reminder for myself. So that will take 20 hours here. And if you have, which a lot of people do in academia or other places, they have a few computers that sit idle, and you say, hey, I want to use those too. So as long as you can SSH into them and you have R installed, you can actually start using those. And that would be, that works if not too many people are trying to use that at the same time. But as soon as you have multiple users, multi-tenant environments, you need some more orchestration, and that's where job schedules come in. So the end user, or you using that cluster environment, you don't have to worry about running other people over with your jobs. It will just work. And just to show what it looks like, the bare bone command line, this is not R, this is shell. So this is a shell script, and it calls an executable hdseq align. It takes one argument and a human reference. And then it has some declarations up there to the job scheduler, say I want 12 gig memory, and I want to have this name. So this is how you submit 2 patients to that job scheduler. Queue sub, you add it to the queue, and it will sit there and wait. The scheduler will make sure, are there any computers available? No, we wait, and then you submit them to the different computers. And then you can look at the list of other users running. So a lot of people do this. So there's this beautiful package called the batch tool package. It's been around for several years in R that tries to encapsulate this in R. And then I used that for a long time, and then when I wrote Future Framework, I wrote a wrapper around this that implements the future, the resolve, and the value functions to the batch tools. And now I can use this. The only thing that replaced from the previous line where I run parallel with my local computer is that planned batch tool SG. SG is one kind of schedule, and this will now distribute it out on the compute cluster, assuming that all the compute nodes has access to the files, of course. Yeah. And then I can basically, if I have enough computers, this will take 3 hours at most. Everything runs at the same time if I'm lucky. So again, here is, yeah, so I will repeat this. It's like the end user decide how to parallelize, you decide what to parallelize. So here is another, I would say, backend. Mark Edmondson, CloudER project. They made it simpler and simpler, so now I think this is they really nailed it. The Google Compute Engine R. As long as you have set up your account with Google Compute Engine, this is the code to launch 36 machines in the Google Cloud, and then tell the future framework that I want to use those 36 machines as my workers there for parallelization. And this is a toy example how using Monte Carlo how to estimate pi. So it's a function called Monte Carlo pi, and each of the rounds did 10,000 simulations, and I do hundreds of those. And when it's done, I reduce that and I get an estimate of pi. And this is the code that launches machines in the cloud, puts the work out there and brings it back again. And there's similar work for Amazon. Okay, call it no animation, sorry, it was too old. I wanted to see this one. But Futures in the Wild, I call it. It's just some, I mean, I showed you how this very basic thing, like you can do a simple future, simple things, send them out, and then there we have the map reduce or the apply functions. There are higher level APIs that builds on top of the future framework where they make workflow manager, basically Unix make in R. Drake really grown and became a solid solution for this. It is now under our OpenSci project. So basically define different tasks you want to do, and nothing runs in the first expression, the first part up here, but it declares the dependencies. And if you follow the code, you will see that the first raw data and data depends on raw data, hist depends on data, and fit depend on data, but fit and hist doesn't depend on each other. So those two can be run in parallel if you want to, as long as data is available. And then there's a report that is not clear here what they depend on, but for their code inspection it depends on other things here. And they just, the way you do in Drake, you say, make these tasks, complete them, and use future as a parallel backend and use two workers. And it will resolve this as fast as it can. So it's not like an lapply call, there's much fancier things going on underneath there. But they all work on the future function and the value function, basically. Yeah, that's a graphical illustration of that parallels here. So dependencies, and these two can be done as soon as that one is done. Shiny last year came out, Shiny 1.1, how you can do asynchronous things, and the future framework provides the underlying background parallel processing. There are much more to it on top of this too, but it's just those very simple functions fits into that framework, so we could just plug and play this one in there. Okay. More puns, near future. So there are several things that feature requests, and this year, last year too actually, one thing was like if you have an expression that outputs something to the terminal, print or cat or something like that, we added, so even if that's done in Australia, on a machine in Australia, that output is now brought back and relayed on your local machine in a consistent way. So that's the critical thing. You don't want it to, like, if it runs on the local, you might see it, but if you run it there, you might not see it. So this is like works the same regardless of the backend. So that was major work. And then the similar idea with like relaying messages, which is standard error, basically. But also warnings, so if there's a warning generated somewhere, that's relayed to a local machine in a consistent way. Error message in troubleshooting is complicated. Some work on that. Good. Time is running out. So there is a proxy for doing traceback that you kind of can track it even if it went around to Australia and back. It's not perfect, but it works. Benchmarking. Now these are like some of the features are fairly simple to do and some are very hard because it's more a design issue. Benchmarking is something The snow package has a nice solution for that. If you parallelize things, you can get a plot later where your different expressions spend time. Are you like actually using the workers or a lot of idle machines? So now we're recording when a future started and when it stopped. Hook functions, this is number one. Progress bars. I want progress bars. And asking that means many different things for different people. And the reason why it doesn't exist is because I'm a perfectionist. No, but I don't want to tie into a specific progress bar solution, or what does it even mean by progress bar. Maybe it's a logging function. Maybe you want to say, I got to this point and this point. You're not necessarily just a progress bar with numbers. You might want to convey more information. And I think the solution to do that is to provide hook functions and then having other people in the community tie into that to provide their favorite progress bar. Maybe the progress bar will be a message on the cell phone or on your local machine and graphical user interface or audio. So killing futures, if you start something in Australia, again, you don't have to worry about it, but they complain a lot down there. And that might run for years. So is there a way for me to kill it here while in my R prompt? You can do that in some backends, but not all. So how do you find an API that works in both? So that's like an optional feature. And then we're starting failed futures. It's related to this. I want to mention that the for each Rich Callaway, they have a version of for each. It's actually out there, but you have to search for it. That actually they decided to use the future framework to identify global variables. So that's great, because that means now these two frameworks will be a little bit more similar from the end users and developers' point of view. You don't have to worry about different things. Okay, who's the timekeeper here?
2 minutes.
Okay, and no questions after 2. Okay, okay, good. Okay. I can just mention there are other things we have to worry about. Is like some future can only run when there's a GPU or if the file exists. So this is like resource management. I don't know if this should be in the future package because you might reinvent like the whole thing that schedulers do or not. So this is like design decisions, like dangerous to implement, although they might be simple in the first view. So we're holding back on that. But another thing that I'm keen on, you can sandbox future evaluations with containers like Singularity and Docker. You can actually get code from someone you don't trust and run it on your local machine because you have the power, compute power, and you don't have to worry about the risk of running that anonymous code. That can be wrapped up in this too. I don't know if it's a wise thing to do, but it's possible. Okay, so the summary is unified API with futures, portable code, you don't have to worry about it. Developers decide what to parallelize, user decides how. And I want to say thank you for that. And if there's one question.